Hi, welcome back. Some of the questions in exams are similar. In exams, there will be, for the first term, for the first midterm at least, there will be no like very long proof questions that ask for like proof for a asymptotic properties like big theta, big O using substitution methods. There won't be questions like that. There are more questions about reading, analyzing the pseudocode, and filling the necessary blanks in the pseudocode to achieve certain functions. So I will make so according to our schedule, next Tuesday we will do a brief review about the first midterm, but I'm now thinking about I will move the review probably to this Thursday so that you will have more time preparing for it. Yeah, so I will make, that's what I'm considering now. So I will make announcement later. All right, so let's get started. And today we will talk about the second sorting algorithm, heap sorts. So it is a very commonly used algorithm. And compared with quicksort and merge sort, it also has a very efficient running time bounded by n times logarithm of n. And it is also a sort in place. It doesn't cost extra memory space like merge sort did, like merge sort does. Okay, it's so from this perspective, it's similar to insertion sort and quicksort. Okay, but one advantage of heap sorts over quicksort is that in quicksort we have a lot of recursive calls. So we have the quicksort. After we partition the sequence into two segments, into two sub-areas, we need to call the quicksort function recursively, right? We need to call quicksort function recursively, which means there's a lot of recursive calls, and the recursions, when the recursion happens, we need to use the stack in the computer memory, and basically the stack calls back will cost a lot of time, and also stack memory usage is not as sufficient as the heap usage, the memory in the heap of a computer system. Yeah, so heap sorts, on the contrary, you will find that it doesn't use a lot of heap sort, it doesn't use a lot of recursive calls, and it is also a memory efficient method, algorithm. So the core idea is that we will need to use a data structure called heap to manage information. Basically, the input sequence, the inputs array will be basically viewed as a heap data structure, will be programmed into a heap data structure, and then we basically move elements around within that heap. Okay, so in order to understand heap sorts, we will start with the heap data structure. Okay, so let's see what it is. And the heap we use in this case, in a heap sort, is a binary heap. It is looks very likely to a complete binary tree. Okay, this is a typical structure of as a showcase for a heap structure. So we have, open the pen here. We have the numbers above each circle node. It's the index. That's the index, just like the index of array. Okay, so this is the first element, second, third, fourth, fifth, and so on. So the index, if we look at the heap within the tree, then the index like is from upside down. It's like a first row, second row, from left to right in that order. Okay, and the values of each elements in the heap is in the circle here. Okay, so and in the physical memory space, we don't actually have that actual tree structure, but we can basically put the heap into an array. Okay, and there's no difference from an input array from the array if we just look at it as it's no difference other than a sequence of numbers in your memory. Okay, and the relationship between a root node or between a parent node and its children can be indicated by these lines here. Okay, but these lines, they are all now currently imaginary. Okay, we can imagine that the 14, the index, the elements A2 is the left node to A1, and the A3 is the right node to A1. Okay, so we can visualize this in our mind by think of the children node appending to the right of the array. Okay, so you see that the organization of the array is like this. The first root node came in here, then it comes the left node of the right node of the root node, and it comes the left node and the root node of the first left node, right, and so on. Then 9 and 3 are the left and rights for the first right node. Okay, so such an organization will allow us to store the elements in a heap using a linear space in computer memory, just like an array space. But we just need to memorize some properties. First of all, it's the length. And this length is no different than the length of an array. Okay, so this A dot length is simply the number of elements in the total array, in the whole array. But not all the elements in the array are necessarily the elements in the heap. Okay, so here we need to differentiate the array here and the heap. Okay, so the scope of the heap is defined by the property heap size, and this number indicates how many elements in the array A can be counted as heap elements. Okay, anything beyond or any elements beyond the range of heap size do not count as heap elements. Okay, so that's the two important properties we need to use. And when we represent the heap, basically we will not just represent how many elements are there can be counted as heap elements. For example, we use the heap size, right? So elements from 1 to heap size. And this heap size is always bounded by the length. It cannot be larger than the length because we will never go beyond the range of the allocated space in the array. Okay, and more importantly, we want to model, or we want to describe the relationship between the root node and its left child and right child. So given a parent node, we want to know where its left child and the right child are. So the roots is A1, and that is the very top elements in the heap. Okay, and given any index I of a node, we can compute the indices of its parents, left child and right child with these helper functions or helper procedures. So we have a first procedure called parents. Okay? So it tells you that given the node at index I, we should return half of I rounded to the floor as the index of its parents. Okay, so looking at the element, the second element here, the index is I. Half of I is 1, rounded to the floor is also 1. So index 1 is the parents of element 2. And for 3, half of 3 is 1.5, rounded to the ground, rounded to the floor is also 1. So that's why we can have these connections. And for 7, for example, for the index 7, half of 7 is 3.5, and rounded to the floor will result in 3. So the third element is the parents of the 7th element here. Okay. So that's how we compute the parents. And for the children's relationship, like if we want to know the left child of an index I, we simply return 2 times I. Okay, and for the right child, we simply return 2 times I plus 1. Okay, so for the index 4, its left child is 8, right here, indicated by this connection, and its right child is 8 plus 1, which is indicated by this connection. Okay, that is how we do the use the helper functions to remember the parents and the child relationship in the heap. Okay. So these are basically the building blocks we will need to use in a heap. All right, so now let's the second bullet point. I mean these bullet points, right? Only the elements, okay? Only the elements within this scope, okay? They are valid elements of heap. So what I mean by this bullet is that to an array, there could be more elements than the current limits of heap size. So for example, if the heap size is here, so the heap size is 10, so it basically says that within the array, the first 10 elements, they can be viewed, they belong to the heap. They are the heap element, but everything beyond from index 11 on, these elements, they are still in the array A, but they do not count as the heap elements. And the heap really ends here. Okay, so the elements to the right, they don't conform to the rules or the principles of heap elements. Okay, so this heap size property is important in the next steps when we do the heap sorts, because we can shrink the size of the heap by decrementing the heap size by 1, right? When heap size, when we drop the heap size, we decrease heap size by 1, we'll basically kick out or drop 1 element from the heap. Okay, so there are 2 types of binary heaps that are commonly used: max heap and a minimal heap. So a max heap is a heap that satisfies that for every node, okay, other than the root, the parent of it is always greater than itself. Okay, because the root node doesn't have parent, so the only exception is the root node. Okay, but to the root node, it's always greater than its children node. Okay, and the left child is always greater than its own left child and right child. Okay. Or let's put it simply, in the max heap, the largest element is stored at the root node because it's greater than its children node, and the children is greater than the children's children, and so on. Okay, that's max heap. And the subtrees rooted at any node contain values no larger than a node itself. Okay, so and each subtree or subheap is also a max heap. Okay, but a minimal heap is the other way around, on the contrary. So for every node, its parent node is always smaller than the node itself. Okay, so the smallest node is stored at the root. Okay, and for heap sorts, we will need to use the max heaps. Okay, but the minimal heap is also quite useful. For example, in the future, when we talk about graph algorithms, we need to use a minimal heap for implementing a priority queues data structure. Okay, so that's max heap and a minimal heap. So the focus of heap sort is using max heap. Okay, and now let's talk about the height of a heap. Okay, so let's first define the height of a node. Okay, for each node in a heap, we say we use the number of edges on the longest downward path from the node to a leaf. Okay, a leaf is the most bottom node. A leaf is the nodes that don't have children, so it's always at the bottom. So in this case, the most bottom 3 ones, they are the leaves. Okay, so the height of this node is 1, because from the node 8 to the leaf here, it's just 1 edge. So that's 1 connection, we call it an edge. Okay, and for the leaf here, the height is 2, because there are 2 edges. Okay, the leaf node at the root is 3. The height of the root node is 3. Okay, so we can use the height of the root node to define the height of the heap. Okay, so if we say that a heap, the height of a heap is 3, we are basically saying that from the root node to the longest, to the deepest leaf, the longest downward path is 3. Okay. All right. And another actually important property, this one, okay, is something we will utilize when we analyze the running time efficiency of heap related operations. The heights of a heap that contain n elements is bounded by the logarithm of n. Okay, so in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, we have 10 elements. So the logarithm with base 2 of 10, right, is 3 point something. Right, so that's exactly the heap. That's the height of this heap. All right. So let's looking at some basic operations on a heap. So previously we already talked about the parents, the left and right procedures to help identify the parent's node or the left or child node for any given node. Okay, but now we're looking at a bit more complex operations, but which are also the basic building blocks for the heap sorts. Okay, so the most basic operations on heaps run in time that is proportionate to the height of the heap, which is logarithm of n. So that's why I say this logarithm of n is an important property. I would say most of the operations run is bounded by the this upper bound, which is good because it's even better than the linear time function, right? So, for example, the first example is MAX-HEAPIFY. So we'll analyze that for the, I'm talking about the question, would a logarithm of n be an average case? Yes, in most cases, it's an average case, not best case, because the heap is quite consistent data structure. That's the average case. The logarithm of n describes the average case of the most heap-based operations. So, for example, the first one, MAX-HEAPIFY, as the name indicates, this procedure will maintain the heap, the max heap property. Okay, so given a heap that is not input heap, that is not necessarily a max heap, applying this function on that input will result in a max heap. Okay, remember the max heap always have the larger parent node than the root node for all the nodes in the max heap. Okay, and the second function, build max heap. Okay, this procedure need to call the MAX-HEAPIFY. Okay, it produces a max heap from a totally unordered input array. Okay, so it's quite different from the MAX-HEAPIFY because MAX-HEAPIFY needs to be called on an array and an index. It will make the heap that rooted at that index to become a max heap, But the build max heap does more than that. It will, given an unordered input array, it will produce a max heap totally out of unordered elements. Okay, so and within the build max heap, it will call the MAX-HEAPIFY. So that's why the build max heap runs slightly slower, which is bounded by a linear running time function. Okay, and another one is the heap sorts. That's we will that is actually the topic, the main focus here. It runs in n times logarithm of time. So as we may guess now, the heap sort needs to utilize the MAX-HEAPIFY and the build MAX-HEAP procedures. Okay, so next we got to know about all these procedures step by step. So first, MAX-HEAPIFY. As I said, the function, the procedure needs to take an array and an index I. The index indicates the position of the root node of the max heap that we need to MAX-HEAPIFY, called MAX-HEAPIFY on. Okay, and also this procedure comes with assumption. It assumes that the binary trees rooted at left node and the right node, they are already max heaps. Okay, so it assumes that I don't care about the left node and the right node, because I assume that the left subtree and the right subtree, they are already max heaps, and the procedure only cares about if the roots, or if the parents, if the current root at index I is greater than the left child or the right child. Okay, the current elements at AI, it might be smaller than its left child or right child, and in those cases, it basically violates the max heap property, because the max heap needs to have the parents to be larger than the children node. Okay, so the overall, this MAX-HEAPIFY will let the elements at index I flow down in the max heap, okay, so that the subtree rooted at index I obeys the max heap property. So if the element at AI is a relatively small element, if it's smaller than its left child or right child, it will let that element to flow down. Okay, so let's look at the pseudocode here. So let's quickly look at each line of the code. Okay, first two lines, it simply calls the left and the right procedure that tells us where its left child is and where its right child is. Okay, so the L and R, they are indices for the left child and the right child. Okay, then it comes one if and else, the second if, right, the third if. Okay, so it's just the three if conditions. Okay, and there's in the last if, there's a recursive call, MAX-HEAPIFY, to itself. Okay, so next we'll look at what this if conditions does. Okay, let's put the pseudocode here. All right, so let's look at the first two if else conditions. Okay, so from line 3 to 7, well, let's look at the line 3 to 5 first. Okay, so it's the first if, it compares, so it first checks whether the left child is within MAX-HEAPIFY. Okay, if L is outside is outside the heap size, then we basically don't need to consider it, because it's beyond the heap size, it's beyond the valid range. Okay, so if L is still within the heap size and the elements in the left child is greater than the current parent node, then we will need to record that the largest one is the left child. Okay. Otherwise, we don't. We will let the current node to be the largest node. Okay. And the second if is simply to compare the largest elements with the right child. If the right child is larger, then we'll record R to be the largest elements. Okay, so basically, the line 3 to line 7, the first two if conditions will determine the largest elements among AI, the elements at the top, that is the current elements, and the elements in the left child and the elements of the right child. Okay, so and the largest index will be stored in the variable called largest. And in the coming, so if AI is the largest, okay, so the next if condition will compare whether largest equals I. Okay, so if the AI is the largest among the three elements, then we don't need to do anything. It's already satisfied the max heap property. Okay, max heap requires that to each node, their parents should be larger than all the children, right? So we only need to deal with the case where the largest is not the current node. Okay, so here the next steps is critical, because if either one of the two children nodes has the largest elements, then we need to swap the elements in AI with the largest elements. Okay, which will cause the node I and its children to satisfy the max heap property. Okay, so
wait a minute, that doesn't make any sense. Wait a minute, can you hear me?
yes.
Okay, like what does it say if largest not equal to I? Isn't I like an index? Shouldn't that be AI?
Yeah, so if largest doesn't equal I, means that AI is not the largest.
So like shouldn't be largest not equal to AI instead of I for like
No, largest is
contextual
not the
like
value,
sense?
but largest is the index of the largest element.
Okay, but isn't I also an index?
Yeah, I is also index.
Okay, so the largest is the index. Okay.
Yeah, largest
Okay,
is
so it's
the index, is not the
okay,
value.
so it's another index. Okay.
Yeah. So if I is not the largest elements, then we basically need to exchange AI with whatever the largest is. It could be the left, it could be right. Okay, so we exchange AI with the largest elements. And so in that case, now within these three elements, AI, AL, and AR, they satisfy the MAX-HEAPIFY property. Okay, but we are not done yet with after we exchange AI with the A largest, because now we need to consider the node indexed by largest, right? Because we have switched AI with A largest, and now this new root node for this subtree, it might violate the MAX-HEAPIFY property. Okay, because we previously assumed that the left subtree on that child node is already a max heap. But after we switched its root node with its parents, then the root node for this current child tree is has a new value in this root node. So it's not necessarily a max heap. So that's why we need to call MAX-HEAPIFY on these largest elements again, and this is a recursive call. Okay, because we need to make the subtree rooted at the largest now to make it again a MAX-HEAPIFY. Okay, So next we will use a concrete example to show why MAX-HEAPIFY works. I believe after we have seen the example, it will be much more clear than just reading the code here. Okay. It's heap dash size. Okay. So let's look at this example. So given a heap, first let's check whether it's a max heap or not. So apparently it violates the max heap property because the parent's node here is smaller, has smaller value than its children. Okay, so the subtree, this subtree, it violates the MAX-HEAPIFY. Okay, so now, and we'll assume that all the data are stored linearly in the area A here. Okay, and the heap size is 10. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements here. Okay, so the inputs is A and the index is 2. Okay, and the goal is to make the subtree rooted at index 2 to be a max heap. Okay, right now it is not a max heap. Okay, and it also assumes that the left child and the right child is already a max heap. Okay, so again, it's not shown here, but we need to remember that the MAX-HEAPIFY relies on two assumptions. So it assumes that these two, they are already max heaps. Okay, if not, then we cannot call this procedure properly. Okay, so what the MAX-HEAPIFY procedure does is to first get the left child index, which is 4, okay, and the right child index, which is 5, okay, right? It indicates the 4 and 5 here, and because among these 3 elements, A4 is the largest. Okay, so we basically need to switch the elements A4 with A2. Okay, because the subtree we detect a violation to the MAX-HEAPIFY property, max heap property. So we need to switch or exchange A4 with A2, right? This is the largest one. We need to switch with this one. Okay. So what would happen after we switch is that we need to call MAX-HEAPIFY on that A4 again, because this is how it looks like after we switch A4 with A2, because now the new A4 is 4. Okay, and the value 4 here also violates the MAX-HEAPIFY max heap property here, because it's smaller than the 8, right? That's why we need to call MAX-HEAPIFY on these elements A4 again. Okay. Okay, we need to call MAX-HEAPIFY on A4 with this left child, and its left child is 8, and the right child is 9. Okay, and we find that A9 is the largest one. So again, we need to exchange A9 with A4, right? and then call MAX-HEAPIFY on A9 again, according to the pseudocode implementation. Okay, so now our elements 4 is at the bottom of the heap now, right? Now we need to call MAX-HEAPIFY on A9, okay? And we'll find that if we use the left helper function, the right helper function will compute the L and R into with new values of 18 and 19, okay, which is beyond the size of the heap, okay, which basically tells us that, well, this time the A9 is already a leaf node. It doesn't have children nodes. So we basically need to stop here because the max heap property is already satisfied. Okay, no further exchange need to be made. Okay, so through this example, we have shown here basically the elements that are here currently was originally here. Okay, so what we do with this one, with this subtree, is to let the elements 4 flow down, okay, according to some sequence. And after each time it's switched with the correct child node, we need to call MAX-HEAPIFY on that child node again, because we are not sure if that new child tree satisfy the max heap property. Okay, so in the next slide, there will be an animation which basically shows that if we call MAX-HEAPIFY on A2, so here we have the original shape and the values of the max heap. We let the element A2 to flow down to a proper position. Okay, so the 4 was here, and after we call MAX-HEAPIFY, it will flow down, and the resulting other elements, they flow up to the correct position. Okay. So now if we look at the subtree, again, it's now obeys the max heap property. For each node in this subtree, the parent node is greater than the children nodes. Okay, so we have achieved the purpose of making this subtree a max heap by calling MAX-HEAPIFY. Okay, so that is the running time analysis for MAX-HEAPIFY. So before we proceed on to the next operation procedure, we analyze the running time of this MAX-HEAPIFY a little bit. So intuitively, there are no for loops, right? All we have is a bunch of if and else, but the critical parts is the last if condition, in which we have a recursive call to the function itself. Okay, so there's a recursion here. So that means we need to use the recurrence equation to describe the running time of MAX-HEAPIFY, right? So it basically it's a sub-problem here. When we call MAX-HEAPIFY on the largest index elements, we are running the same function on the smaller subsequence, or on a smaller subproblem. But only if we don't, the only difference is that we don't know the size of the subproblem. Okay, it is not like evenly splits the original problem into two subproblems. It's not like that. But there are ways to estimate the size of the subproblems. Okay, so we can everything above line 10, they are constant time. It's just if and else comparisons. Okay, so the question is, what is the size of the subproblem? Okay. Does the Heapify violation starts the process on the right tree? A11. Not sure what do you mean by A11, because in the previous example, the 11th elements is beyond the heap size. Okay.
Yes, Professor, I was just wondering, in like a hypothetical situation, if you added that additional 11th element and it was 15, since that original look is going to see, okay, 14, we're going to want to move that up just based on the initial configuration of the tree. If there was a 15 at position 11, so it's going to do all the same things that it does to get that 4 down to position 9. But at the end of that, does everything check again to see if everything's in the correct order and then perform that process again on that right subtree?
So in this case, if the A11 has a value of 15, then we cannot call MAX-HEAPIFY on A2 because the right subtree is not a MAX-HEAPIFY yet.
Oh, okay, gotcha.
Yeah, we first basically need to call MAX-HEAPIFY on this node, on A5. So first we need to make it MAX-HEAPIFY. Right. So yeah, that's a good example here, though. The assumption of MAX-HEAPIFY is that the left child and the right child trees, they are already max heaps.
Okay, thank you.
Yep. So let's continue the question of the running time of MAX-HEAPIFY. All right. So when we consider the size of a subproblem, because now the subproblem is a subtree, right? It's a tree structure. It's actually the question of what's the size of the subtree rooted at the node largest. Okay? Because now we can only estimate the size of it because we cannot iterate over all possibilities, right? That's it's just a random inputs arrays which we cannot know the subsize for sure. Okay, we can assume that the subproblem is sort of the n over b size, but we don't know what exactly b is. Okay, we can only estimate the size of b, or we can try to estimate the range of b, to the most extreme cases, how big or how small the subproblem, the size of subproblem could be. Okay, so let's first analyze the most balanced case. Say the tree is a complete full binary tree. Okay, so in this case, the recursive call is either on the left subtree, okay, on the left node or the right node, they will result basically the same subproblem size because it's a very balanced binary tree. On the two sides, they are of the same size, okay? And the bottom levels is full, okay? So if we let n be the size of the subtree rooted at the node I, then the size of the left subtree is equal to the size of the right subtree, okay, which is n over 2. Okay, say we have n in total, and on the left it's n over 2 to the floor, and on the right is also n over 2 to the floor. Right, that is obvious, right? Because it's just two splits with only the root node left out. Okay, so in this very balanced case, the subproblem is n over 2 to the floor. Okay, and the constant is the if-else comparison steps. Okay, so of course it's bounded by n/2. Okay, so this is something now we can analyze using master theorem, and the A here is 1, right? And the B here is 2. So the logarithm of base B of A is 0, right? And the n to the power of 0 is 1. Okay, so the polynomial function is at the same order as this function. So that's the case 2 of master theorem. We basically need to use constant times logarithm of n to indicate the running time for the solution, right? And if we look at the unbalanced case, okay, so if this is the most unbalanced case, that's the left tree has more nodes, right? The left child has more left subtree has more node than the right subtree. So in this case, it's the worst unbalanced case, and the bottom level is half full. So the right subtree has one less level than the left subtree. Okay, so in this case, it has 3 nodes on the right, and 1, 2, 3, 4, 5, 6, 7 nodes on the left. Okay, so assume that the right subtree has k levels. Okay, and the number of total nodes in the right on the right subtree is 1 plus 2 plus 2 to the power of 2 until 2 to the power of k minus 1. Okay, so which is let's indicate it by r. Okay, and because the left node has one more level than the right subtree, so to the left node, it is the summation from 0 to k, not k minus 1. So now the result is 2 to the power of k plus 1, which is almost twice as many as the right node. Okay, so that is also the interesting place of a tree structure. When you have one level of the tree nodes, it's the total number of elements almost doubles compared with a shorter trees. Okay, so the number of the left subtree almost doubles. Okay, so in those cases, the total of nodes is almost 3 times the nodes in the right subtree. Okay, so if now let's consider both situations. So if in this case the right child node has the largest elements, then the results recursive call will on the right subtree, and the resulting subproblem will be n/3. Okay, and if it's the largest, the largest is the left child node, then the subproblem will be 2/3 of the original problem, is 2 times n/3. Okay, but in either case, the coefficient here is 1, right? Anyway, we can use this boundary to describe the recurrences. Okay, we have the coefficients a equals 1 and b equals 2/3. So the logarithm of anything with the logarithm of any base of 1 is always 0. Okay, so in either case, the total running time, the solution, is described by the logarithm of n function. Okay, so it's basically the same running time upper bound with the very balanced binary tree case. Okay, so we can basically conclude that the running time of MAX-HEAPIFY on the tree that has n elements, then we will say it takes roughly logarithm of n time. Okay, so thinking of the problem from another perspective, because we have just observed that when we call MAX-HEAPIFY on index I, we will let the elements AI to float down to the correct position. So in the worst case, the AI will flow all the way down to the leaf node, right? And we know that we let h to be the height of node I, then the running time of MAX-HEAPIFY on it is proportionate to this quantity h, right? OH. We can use the big O of h to decide to indicate the roughly how much time it will take, right? But we know that to a MAX-HEAPIFY to a heap, the height of a tree, the height of a heap is almost to the logarithm of n, the logarithm of the elements in a heap. So that makes sense to use the big O of logarithm n to describe the MAX-HEAPIFY's MAX-HEAPIFY running time efficiency. Okay, so this is a more intuitive, but not that careful split of different cases. But it also helps to have a reasonable big picture of how the running time actually happens. Okay, so with this MAX-HEAPIFY procedure, we can use it to build a max heap. Okay, so we can use MAX-HEAPIFY so to in a bottom-up manner to convert an unordered array, okay, from A1 to AN into a max heap. Okay, so this time the AI input is a totally unordered array. Okay, and the question is how. Okay, a naive solution is that we can simply call MAX-HEAPIFY procedure on array elements, right, from A1 to AN, but that is not correctly or not necessarily the case, because the solution has much more redundancy. Okay, because the elements in the sub-array actually basically from the middle to the right, from one to the right of the middle element to the rest of the elements, they are leaves of the trees. Okay, there's no need to call MAX-HEAPIFY on those leaf nodes because they only have one element, right? Because if you look at the previous example here, all these nodes, they are leaf nodes, and there's in total 11 elements in this tree, right? And 11 over 2 is 5, and 5 plus 1 is 6. So this node is already a leaf node. So there's no need to call MAX-HEAPIFY on this leaf node. Okay, so we can simply skip all the leaf nodes when we want to make a whole max heap. Okay, and we just need to. That means we just need to call MAX-HEAPIFY on non-leaf elements. Okay, so basically, the build MAX-HEAPIFY procedure looks like this. Okay, we will need to first indicate or initialize the heap size because we want everything in the array to be in the heap, we need to indicate that the heap size is equal to the length of the elements. And we will start from these elements in the middle down to 1. Okay, and we call MAX-HEAPIFY on each non-leaf node. Okay, and this down to 1 reverse order is also critical. Okay, because we need to start from a bottom up manner, start using a bottom up manner, because MAX-HEAPIFY has assumptions. It assumes that its children nodes are already heapified. Okay, are already MAX-HEAPIFIed. Remember the assumption. So if we start with the root node, then we don't know if the left tree or the right tree they are already heapified or not. But if we from a bottom up, if we choose the most if we choose the shortest or the lowest level non-leaf node to make them a max heap, and then it'll be safe when we later on reach the parent node. Okay, because the parent at this time, the parent's node already knows that the children node must already have been max heapified. Okay, so let's quickly go through the example here. So given an input of basically random numbers, okay, that is the random input array, okay, and how do we make it a max heap? We'll basically start from the position. So this is a typo here that I need to fix. The length is 10, and half of the length rounded to the floor is 5, not the length. Okay, it should be half of length. So we call this build max heap on A. We will start a for loop from A5 down to A1, right? So the A5, when we call MAX-HEAPIFY on A5, we find that it's already a max heap, right? Because the 16 is greater than 7. And in next iteration, we call MAX-HEAPIFY on A4, and we found that it violates the max heap property. So we need to let A4 flow down to the correct position, right? And let the 14 elements flow up. Then next iteration, we'll need to go to these elements, A3, right? And A3 also violates the max heap property. So we need to float 3 down and 10 up, okay? And next is A2. A2 violates the heapify max heap property. So we'll let the A2 to flow down, okay? Which will follow the correct position, right? And the 16 will be moved up and the 7 will be moved up, okay? So the last element, the last iteration is A1, which violates it, the max heap. So A4 will flow down here, right, to the correct, along the correct path. All right, so after all these iterations are done, we have a max heap built up, okay? So now the whole array is a max heap, and the heap size is the length of the array, okay? So as you see, we call the MAX-HEAPIFY procedure iteratively in order to make the whole heap a max heap, the whole array a max heap. Okay. The difference is that it's not sorted. You know, it's not sorted. It looks like a reversed order, but it's not strictly sorted because we are not sorting the algorithm. We're not sorting the array yet. We're just making them max heaps. But we are now one step away from the heap sorts. Okay. So first, let's analyze the build MAX-HEAPIFY, build max-heap procedure a little bit. Okay, so it's a for loop now, right? It's a for loop. Okay, and within each iteration of the for loop, it's a MAX-HEAPIFY. We know that MAX-HEAPIFY costs us the logarithm of n times. So it makes sense to say that it's n times logarithm of n, right? So, but this is not a asymptotically tight upper bound yet, okay? Because after we analyze the procedure really carefully, we will find that it actually takes less than that. It takes less than n times logarithm of n, okay? So if we want to analyze the tighter bound for build max heap, we basically need to observe the running time each time MAX-HEAPIFY is called on the node I, which is of height h. Okay, and so because we know that a heap of n elements has height logarithm of n, and the number of nodes at height h is almost this quantity. Okay, so I would say almost because I use the upper bound here. So when h equals 0, you will find that n over 2 to the upper bound is the number of nodes at height h. Okay, so this is something you can try it on the simple examples at home. So the total cost is actually bounded by this quantity, the number of nodes at height h times the big O of h. Okay, and this summation actually has a tighter bound than n times logarithm of n. Okay, if we compute the summation of this series, it'll be actually a linear time upper bound. Okay, and which is better than the n times logarithm of n. So that said, we can build the max heap from an unordered array in linear time. Okay, which is very good news for us. Okay, so now we have introduced MAX-HEAPIFY and the build max heap. The next step is to implement the heap sort algorithm. Okay, and I think I will gonna put this part, put the heap sorts into the next Thursday's as next Thursday's contents. And so in next Thursday, we will introduce heap sorts, its implementation, analyze it, and then we will talk about the midterm exam. We'll talk about the scope, like what will be tested. So what I can say now is that the sorting algorithms, the quick sorts, heap sorts, and the linear time sorting algorithms will not be tested in the first midterm. Okay, so next Tuesday we're gonna do lecture. I'm gonna give a lecture on linear time sorting algorithm, and on next Thursday it will be our first midterm exam. And that's it. And there will be a office hour on Wednesday, and I already contact our TA. He will also give a office hour in a different period of time, which I will make announcements.
Is he though? Because last week you said he would, but he didn't do it.
Yeah, sorry about that, because I didn't hear back from the TA last week. And tomorrow I will host my office hour in the afternoon. Answers be posted before the test. Yeah, I can do that. The homework answers.
But does that really help? Because like for the homework answers, there's like 5 different ways to do each problem. So are you gonna be posting more than one way, or are you just gonna post the most optimal way you like see or something?
Yeah, I don't think it will be possible to post all possible ways of solutions. Okay. So I will give some solutions. All right, so I will see you in the office hour if you have other questions. And thank you for coming. I will publish the video and release some quiz questions regarding the heap sorts and the quick sorts quiz to the Canvas page.